All right, this is Honors Algebra 2 Pre-Calculus. We're doing section 4.2 in Pre-Calc, which is the unit circle, although we specifically had a video already on the unit circle that was an entire day of class just to familiarize you with the unit circle and what it is. So in this video, we're actually going to talk about how to use the unit circle. We'll also discuss what it means to be periodic, what even and odd trig functions are, and how to evaluate trig functions on your calculator. So all right, so let's go ahead and get started. So recall that in the previous video, we had this picture of something on the unit circle, right? And we had that if you have a hypotenuse of 1 and an adjacent side of x and an opposite side of y, you can find the sine, cosine, tangent, cosecant, secant, and cotangent, right? So we got these values. We got sine is the y value on the unit circle. So actually, when I denote this, I frequently say y on the unit circle and x on the unit circle and y on the unit circle over x on the unit circle. To be clear that sometimes, because sometimes your problems are going to have an x as the angle, which is not the same as the x on the unit circle, right? So sometimes I'll call it xuc or yuc to make it clear, that what we're looking at is the x or y value on the unit circle. So we're going to find the exact value of all 6 trig functions for this particular angle. So the first thing you're going to do is you're going to find the angle. Now, I gave you a shot of the unit circle that showed that angle so that we could start there, right? So the sine, so on the unit circle, right, the sine, x on the unit circle and the y on the unit circle, that's the sine and cosine. Sorry, but not in that order. So the cosine comma sine, and it is alphabetical if it helps you. X comes before y, sine comes after cosine, right? I said that a little bit backwards, but that's fine. It's been a long day. So I'm going to go ahead and find the sine of theta. I know it's the y on the unit circle. Well, the point I'm looking at, the y on the unit circle is 1/2, right? You don't need that middle step. You can just write that sine of theta is 1/2. I'm just trying to explain to you why I know that, right? I'm going to find the cosine of theta to be the x on the unit circle. Well, that's the √3/2. And again, that's because this theta is pi/6. I can write the pi/6 in there, but since they called that theta, I can call it theta. Now, the tangent's going to be slightly more complicated because the tangent is going to be sine over cosine, or y over x. So I'm going to get 1/2 over a √3/2, which is not a wrong answer, but in this class, you're going to have to simplify. So that's a 1/2 times a 2 over √3. Right? So I'm going to get that this is a 1 over √3, which I would then rationalize and get a √3/3. So I'm going to get that for my tangent. Now, the other 3 trig functions are actually pretty easy because what I'm going to do is I'm just going to flip them, right? So the cosecant of theta is going to be a 2 over 1 or just a 2. The secant of theta is going to be a 2 over a √3, which I would then have to rationalize because we don't leave the root on the bottom. So I would get 2 √3/2. And then for the cotangent, I would suggest that you don't flip the rationalized form. Flip the version that was already, like this was the original version, right? If you flip this guy, it's already a √3/1 or a just √3, and you don't have to re-rationalize. If you flip the simplified version of tangent, you would have to go back and rationalize again to fix the rationalizing you'd already done. So those are my 6 trig functions, right? So sine, cosine, tangent, and then cosecant, secant, and cotangent. All right, so go ahead and give it a try. You can pause me if you want. We are using 3 pi/4, which is this angle, so this is the point on the unit circle that you want to use. So sine, cosine, and tangent, right? So the sine is just going to be the y value, right, which is going to be a positive √2/2. The cosine is the x value, which is a negative √2/2. And the tangent is going to be a √2/2 divided by the same number, but as a negative. Now, you could clean that up like this, right? You could recognize that it looks like this, and then at some point, you're going to realize that it's just a -1. The question is how early you realize it's just a -1, but at some point, you're going to realize it's a -1. So you have your cosine and your sine and your tangent. So then I'm going to flip those 3, right? So if I flip the sine, the cosecant is going to be a 2 over a √2, but we would have to rationalize, right? We can't leave that √2 in the bottom. So I'm going to get a 2 √2/2, which is just a √2. Once you know that that's how that particular value rationalizes, I would argue that you probably don't actually have to do the work for the secant. You could just jump to the answer. If you feel like you do need to rationalize and show the work, that's also fine. one thing you'll start to notice eventually is that all of these values, because there are only about 6 different values on the unit circle in terms of the x and the y, all of them simplify to the same couple things. So once you start to get good at this, you won't have to do all of the simplifying by hand. I certainly wouldn't think it was cheating if you jumped from this step to what the answer is. All right. So we're going to try 180, right? So 180 on the surface seems a little bit easier, right? Because the two values are pretty nice. It's a -1 and a 0. So the sine is going to be the y value. The cosine is going to be the x value. And the tangent is going to be the y on top of the x, which is just 0. But when I go to the flipped versions, so my cosecant theta is going to be a 1 over 0, and the word for that is undefined. That's not, it's not a number. That's not how you spell undefined. There you go. So the word for that is undefined. All right. My secant is going to be a 1 over a -1, which is just a -1, right? And my cotangent is also going to be a number over 0, right, which is called undefined. So you can't leave it as a 1 over a 0 or a -1 over 0. You have to write that it's undefined. All right. You're going to go ahead and try 240, which is right here. Right, so go try 240, find all 6 functions. I'm a little limited on space the way I set up these pages, but I usually write my problems pretty much akin to this, where I write the sine, cosine, and tangent, and then I flip the ones right next to them, so it's easy to keep track. You certainly don't have to do that, but I usually write it something more like this, where the sine, cosine, and tangent are in a row, and then the flipped versions are right next to them, so that I can easily see which one I'm flipping for what. So the sine is just your y value, right? So that's a -√3 over 2. Your cosine is the -1/2. And your tangent is going to be a -√3 over 2 divided by -1/2. That's a -√3 over 2 times a -2 over 1. So I think we just get √3. So there's my tangent, my cosine, and my sine. So cosecant's the flipped version of sine. So that's going to be a -2 over a √3. If you rationalize by multiplying by √3 over √3, you're going to get that this is a -2 √3 over 3. And we've seen that number before. If you flip the -1/2, you're going to get a -2. And if you flip the cotangent, you're going to get a 1 over √3, which you would have to rationalize. And you're going to get √3 over 3. And again, as you do this a lot, you start to see the same numbers all the time, and you don't have to put quite so much thought into it. All right, so let's talk domain, range, and period for sine and cosine. So both sine and cosine have a domain of all real numbers, which we're going to get more familiar with when we graph them in 4.5. And they have a range of from -1 to 1. And that makes sense if you look back at the circle for a sec. Let's go here, right? If we were to look at this entire circle, the x value, the highest the x value gets is 1, and the lowest the x value gets would be -1. And then it loops back towards 1 as the x value, and then -1 as the x value, right? Same thing's true with the y values with sine, right? The lowest the y value gets is -1. It works its way up to 1, and then back down to -1. And so it's cyclical, and it never exceeds that 1 or -1. All right, so these functions are called periodic. A periodic function has the form f of x plus p equals f of x for some x in the domain. The smallest number p, for which that statement is true, is called the period. So what that means is that if you look at this graph, right, or if you look at the circle, let's go back up to the first one. If I go around this circle, right here I have a sine that is 1, right? Sine of 90 degrees or sine of pi over 2 is 1. If I go around the circle again, one full circle later, meaning 2 pi later, I will also get a sine value of 1. Another full circle later, meaning another 2 pi later, I will get the same sine value of 1. So the period of this function is 2 pi. That's how long it takes this thing to loop back around. So this makes a lot of sense. For instance, sine of pi over 3 should be the same as sine of pi over 3 plus 2 pi, because here's pi over 3, right? And pi over, so this is pi over 3, right? This angle in purple. Well, pi over 3 plus 2 pi is literally pi over 3 plus a full circle. It ends at the same spot. So it makes sense that it would have the same y value on the unit circle because it's the same spot on the unit circle. They are coterminal angles. We're going to talk a lot more about the periods of trig functions when we get to 4.5 for sine and cosine and 4.6 for the other 4 trig functions. But for right now, that's all you need to know. All right, so knowing the periodic nature of sine and cosine, we can help evaluate angles that are not on the unit circle but happen to be coterminal with ones that are. So -7 pi over 2 is not on the unit circle, right? But the fact that it's a number, like a pi over 2, means it probably is on the unit circle. It's coterminal with something on the unit circle. So what I'm going to do is I'm going to add or subtract full circles, right, which in this case would be a full period, full circle of 2 pi, until I get an angle I know, so an angle on the unit circle. So I look at this negative 7 pi over 2, right? And I say, what if I were to add a full circle? Well, that would be a negative 7 pi over 2 plus a 4 pi over 2, which is still a negative 3 pi over 2. So it's still not on the unit circle. Although you could logic your way through this one. So then I say, okay, what if I took that angle and added another full period, right? Well, that is going to be a 3 pi over 2, sorry, negative 3 pi over 2, plus a 4 pi over 2. And that absolutely is on the unit circle. That's a pi over 2. That lives right here on the unit circle. This is the point 0, 1. So the cosine of negative 7 pi over 2 is the same as the cosine of pi over 2, which is a 0. Same idea, you're going to try sine of 13 pi over 6, right? So again, 13 pi over 6 is not on the unit circle. Specifically, it's too big because 13 pi over 6 is bigger than 2 pi, right? That would be 12 pi over 6, right? So it's too big to be on the circle, which means I should probably try subtracting a full circle. So 13 pi over 6 minus that full period would be a 13 pi over 6 minus a 12 pi over 6, which is just a pi over 6. So this thing is the same as the sine of pi over 6, which is a 1/2, because this, right, this is my pi over 6 right here. Now, I don't necessarily need to see work on a problem like this, in the sense that if you can look at 13 pi over 6 and figure it out, that's not a problem. But again, it's a skill we're going to want to have moving forward, that we're able to evaluate these angles. All right, that's it for that video.